Okay. Start. So we want to start a new topic. The next 2 weeks or 3 weeks, we will discuss this. Before starting that, we want to start Fourier series. Before starting that, um, I want to introduce something. I mean, talk about something called Hilbert space. You might have heard it. It's basically inner product space, which is complete. That's all. Okay. So since I'm dealing with something called Hilbert space, H is a vector space. We start with the vector space. Okay, and it's an inner product from this. We have already defined this maybe many times, more than once. So this is linear in the first variable, conjugate linear in the second variable. You can take an alpha out. This is just if you have x alpha here, you can take the alpha out, and you can take if you have an alpha here, you can take alpha bar out, and it's linear. That is, if you fix a variable here, and if it is alpha x plus y, you can take the alpha out, and it will be like this. Okay? Alpha z plus yz. Okay? And similarly, if you take some x alpha of y plus z equal to x alpha bar x z xy plus xz. Okay? The second property is xy is equal to yx bar. Then this xx greater than or equal to 0 and xx equal to 0 if and only if x equals 0. It's equal to the 0 element. Anything I missed? I think that's all. That's right. That's right. It's two variables. Yeah, just to see. Correct. Okay. So it's linear in the first variable, antilinear in the second variable. It satisfies this condition and its positivity condition. And I think that's all. So then, if you have an inner product, then you can define norm x equal to, you take the inner product of x and you take the square root of that. Okay. And this will be a norm by using Cauchy-Schwarz inequality, which you know, okay, is a norm. So you only need to prove triangle inequality. Triangle inequality will follow from this. If you want to calculate x plus y, you better calculate x plus y square, okay, because norm x square is this, which is equal to x plus y, and which is equal to, you can calculate that this is equal to norm x square plus norm y square plus xy yx, which will be, because of this condition, it will be 2 times real part of xy. Okay, and this which is less than or equal to, by Cauchy-Schwarz, which is less than or equal to modulus of the lambda 7. Cauchy-Schwarz is norm x times norm y. So this is less than or equal to norm x 2 times norm x norm y. You will get, because of, you do to Cauchy-Schwarz, and you will get this. We have already seen this. Because of this, the triangle inequality will follow. So this is a norm. This is a norm. Okay? And if H is complete, this norm will give you a metric. And if it is complete with respect to this norm, we usually talk about, I mean, completion with respect to a norm. If it is complete with respect to this norm, then H is called a Hilbert space. H is called a Hilbert space. That's all. Hilbert space is just a complete inner product space. Okay. We live in a 3-dimensional Hilbert space, but this can be infinite dimensional. It can be anything. So example, usually we will have only over C unless we specify this. Unless we specify our Hilbert space, our vector space, everything, at least from here onwards, it will be over complex numbers. Okay? If it is over real number, we will specify it. Okay? We will mention it. So this is Cn with the inner product of x1 up to xn, y1 up to yn, equal to summation xi second y bar, yi bar. Okay. There is this confusion between physics and math. Physics, it will be conjugate linear in the first variable, linear in the second variable, but all math texts somehow they haven't changed. So, I mean, it's all this way. Second variable is conjugate linear in maths book, all maths book. So I have to follow this, but it's actually better to have it in the first variable. Huh? Because if you use ket vector, this vector, all the notation will exactly patch up. That's the right thing to do. I think I said this before. Okay. So this is for an example. And in fact, all finite dimensional will look like this up to isomorphism to L2, which is all those sequences. Okay. Xn in C and summation mod xn square is finite. Okay. L2 with inner product of two sequences xn, yn is summation xn, yn bar. Okay. We have seen this also. This is also inner product space. We have seen this already. Okay. And of course, you have to use Cauchy-Schwarz to prove it's a norm and all that, and it will follow. Okay. Okay. Third example is on C0, C of any AB. You take any interval AB. Okay. So on this, if you take f and g, you take two a function f and g in C of AB. Then you define the inner product between them equal to integral a to b f g bar, okay, with respect to whatever. I mean, we will have only the continuous function, so it's Riemann integrable. So f of t, g of t bar, dt. Okay. So when you want to integrate complex function, you can integrate the real function, imaginary function, and then you can, I mean, you can take the I outside of this. Okay. The integral is linear with respect to I, and I mean, that's how you can integrate by definition. Okay. But then C is not complete. Is not complete. Yeah, you will take the completion. Complete with respect to this inner product. Reason you can take this at half. At half, you can take the function till half minus this is half minus 1 by n. Okay, this is half minus 1 by n. Up to here it's 0. From here you just join by a line. Okay, then it is 1. Okay, up to maybe in 0, 1, for example, in 0, 1. Okay, this is 1. You take this kind of function, this kind of functions. So if you, I mean, complete means if something is Cauchy in this, it has to converge. Okay, but these things will converge to this function. If you take this as fn, then fn will converge to the function which is 0 up to half, which is what you call as indicator function of half 1. Okay, whatever. We used this function in the last probability course. Okay, it will converge to that. This is not continuous. The convergence is not uniform. This is not a continuous function. Okay, so I mean, this will converge in what sense? It will converge in this norm. So if you take the integral of this fn, this f is equal to this. Okay, fn minus f square dt. Okay, this will go to 0. This will be just 1 by n times whatever the value which is less than 1. So this integral will be less than 1 by n square, which will go to 0. You can calculate it. Okay. This function f minus fn, so here it will cancel, here it will cancel. Only here it will matter, and the length of this interval is 1 by n, okay, and the value is less than 1. Okay. So it is just 1 by, I mean, less than 1 by n square or something, that will go to 0. So because of that, you have functions fn, which is Cauchy. Of course, if it is if it is convergent, it will be Cauchy. You can verify that it is Cauchy also. Okay. What is closed? Doesn't matter. It's with respect to L2, doesn't matter. Okay. I mean, you can write whatever you want. It will be it, because here we will be, I mean, whatever, when I going to define, we'll consider only equivalence class and it doesn't matter there. Okay? It will converge to this function also in this metric. Okay? So because of that, this is not complete. So we complete it with respect to that. Okay? So when you, I mean, when you complete with respect to a metric, you take all Cauchy sequence and define an equivalence class, you define equivalence relation on that, but you can directly define it for a norm. Okay? And you then you can, I mean, it will be a normed norm. I mean, you have to, it's not just a metric space, it's also a normed linear space. Okay? You can prove that if you work with the same the same way how you proved the completion for a metric space, you can work with normed linear space. Just you can define a norm. You can define, I mean, you have to, norm is just a distance between 0 and f, right? So you can define the same way you can define a norm on that. It will be a normed linear space. Okay? So you can, so you define L2 of AB to be C of AB, completion with respect to this completion. Okay? And we will be dealing with this Hilbert space here, okay, in this class, in this course. Okay, it is just the completion of this. Okay? That's all. This will be actually functions and other things. It's all true, but for us it is just completion. We will be worried only about this, only about continuous function. We will not actually, we will not use any L2 function mostly. All the functions such that what exists. Yeah, all those functions, but what kind of functions? You need, huh? L2, yes, as it is defined as all measurable function, which you can integrate it, and whose integral is less than infinity. Yeah, for that you need to do more. I mean, you need to work. Okay, for to define that integral. Okay, for our purpose. Huh?
You just know that this closure is contained in L2.
Which closure?
CAB.
CAB is contained in that. CAB completion, not closure. Completion I am defining to be L2AB. For us, the definition of L2AB is that. Okay. That will extend to a norm. That norm will satisfy parallelogram. You can actually prove that this actually. So if you take the completion with respect to the metric itself, you can show that this inner product actually extends. For example, as I can see, you can define that if you, on the completion, if you have some x bar, you can define x bar y. Okay, because if you fix one, it will be uniformly continuous function. Okay, you can take some x and converge it to this. Okay, and you can define the inner product like that. Once you have done that, you can define this also. You can work it out. Because the inner product, if you fix one variable, it is linear, it will be uniformly continuous, okay, by the Cauchy. So that way you can actually extend. Okay. Otherwise also you can directly do that also. Huh? Yeah, we need to take the closure. Okay. In converging in, I mean, a sequence in continuous function which converts to that. Okay. I mean, for us, we haven't defined it as a function. We are just taking it as a taking the completion. Okay. It is just to use some tools we need it. Okay. Otherwise, we are not going to work with L2 of AB. Okay. Okay. So this is about Hilbert space. So we say definition. H is a Hilbert space. For whenever I say H, it's a Hilbert space, inner product space, and it's complete. Okay. And H is a Hilbert space. And if you have XY in H, okay, then X is orthogonal to Y. This is the notation. Okay. Orthogonal to Y. See, inner product is some sort of angle. Okay. Inner product is like cos theta. Okay. Okay. It's like angle. I mean, something times some numbers, magnitude times cos, some sort of cos theta. You can see the two real of that. Something like something. It's a notion of that. Yeah, it's like a dot product. Yeah. Okay. So you get it from that. So orthogonal means they are at right angle, something. It's if inner product of x and y is equal to 0. Okay. We say two elements x and y are orthogonal if inner product between x and y is 0. Okay. And second, if you have x contained in H is said to be orthonormal. Okay. Ortho means they are all orthogonal. Orthonormal means for all x in S, norm x, or we can define it like that. Inner product of xy equal to delta xy. That's all, delta xy. You know what is delta xy. Delta xy is 0 if x not equal to y, in 1 if, so if for all xy in S. Okay. Okay. So this is what we call as orthonormal. Okay. 3, subset S contained in H is said to be orthonormal basis. Okay. If it is orthonormal, if it is orthonormal and you take the span of S, you just take finite linear combination of all things in S and then take the closure with respect to this inner product and other thing, that is equal to all of H. Yeah? Finite linear combination. Yeah. What is finite? Linear combination is always finite. If you don't involve topology, how would you take infinite? When you talk about infinite thing, you need to talk about convergence. Okay, I mean, you need to talk about metric or convergence. You need to talk about topology. When we say linear combination, it's only finite linear combination. Infinite linear combination makes sense only if you have a topology. Okay? So span of S is S, H. Okay? I'm just taking closure. This definition. Why I am taking? Because basis will not be, by Bayes' theorem, you will not have a countable basis. To get a countable basis, I am taking closure. Okay. I mean, you have a structure of orthonormal, because I will tell you, I will give an example, maybe it will be clear. Yeah. I mean, Cn will see the example Cn is included in L2. Okay, let's take example L2. L2. On this, you define the sequence En at k equal to delta nk. That is, I mean, En is this 0, 0, 0, 1, 0, 0, 0. Okay. I mean, it goes on. It goes on. Okay. A sequence with 1 at the kth place. Okay. If you take finite linear combination of this, okay, you will get entries in finitely many of them with some scalars, whatever the scalars you want. But you want to get an infinite sequence. For that, you have to take the closure. So if we take span of all those En, okay, then you take the closure, that will be N2. Just work it out. If we take finitely summation lambda n lambda k e k, k equal to some finite, I mean, it could be anything, lambda k I e k I equal to 1 to whatever, n or something, and that will be just lambda in those kth place or something. And if you take the closure of that, you will get all those things in L2. Okay? So this is an example. We'll come to the next example. For a continuous function, we'll come to that, okay, later. Okay, so this is what is called an orthonormal basis. So, okay, let's give another example. We are not going to take continuous functions on, we will take continuous functions on C of S1. Let S1, S is the right, S1 is okay, no? S1 is circle. Z in complex number, mod Z equal to 1. This notation is okay. R dou D, the boundary of the disk or something. S1 is the circle in complex number. Okay, this is a compact metric space. So you can talk about continuous functions on that. So S1 we identify with the interval 0 to pi. We cannot identify, but you have to identify the endpoints. I mean, this modulo this endpoint is identified with the 0. Okay, that is, we don't actually, we don't, this is with respect to e power I theta going to theta. Sorry, e power 2 e power 2 n I pi, right? Going to, is that right? T going to I theta going to 2n I theta. That's fine. I theta. That's all. 2, there is no n. 2n I theta. E power I theta. Yeah, that's all. Okay, there is no 2 pi under the thing. Yeah, right. This is okay. Okay, this map, which takes the same value in the n points. Okay, you are identifying it. Most importantly, if you have a function f in S1, C of S1, or any function, then we identify with a function f in, I mean, we use the same notation, f in C of, see, our Hilbert space is this. From here onwards, no, the L2 will be same. C, let's call this new notation C0 of, I put a 0 on the top. Okay, if you can suggest a better notation, you can tell me. Okay, 0, 2 pi is just all those f in C0, 2 pi, all continuous function, which coincides on that, f of 0 equal to f of 2 pi. Okay, which coincides on the endpoints. I take all continuous function which satisfies this. Then C of S1 to C0 of 0, 2 pi. We have an isomorphism. Okay, so if we have a f here, f of e power I theta will go to f of theta. Okay, if you want, you can put a tilde or something. Okay, f going to f tilde or whatever. Okay, f tilde, whatever. If you have a f here, you define a f tilde by just f of theta. That's all. I'm just identifying this function space with this function space. Okay, that's all. F is defined here, f tilde is defined here. That's all. You just to differentiate. If you don't want to differentiate, I mean, if you are comfortable with not differentiating it, then it's fine. Okay, just if you, in case there is a confusion, you call it f tilde. That's all. F tilde of theta is f of e power I theta. Okay, so we have something between them. Okay, then, so then you, but you will get only L2 because single point and all doesn't matter. Okay, if you close it, you will get only L2. L2 of 0, 2 pi. Okay, let's take this e power, I have 2 pi there, so I n theta. Okay, I mean, yeah, n in Z. Here actually we can have orthonormal basis indexed by anything. Here it is indexed by Z. Okay, is an orthonormal basis for, we'll prove it later. Okay, what theta? This is okay. This function theta going to e power I n theta. There it is Z power n. This is an orthonormal basis for C0. I mean, it's actually C0 is actually L2 of 0. Okay. Or conversely, Z power n, n in Z. Okay, is an orthonormal basis. We have to prove it. We will use Stone-Weierstrass theorem. We'll come to that later. Is an orthonormal basis for C of S1. Sorry, L2 of S1. Again, L2 of S1 is just the closure of, which is C of S1 closure with respect to the same inner product, FG bar inner product. Okay. Yes. From where? No, this is just the L2. This is orthonormal basis. That's clear. Here. So you have C0 2 pi This is just I put a 0 because f coincides in the endpoints, so that you can identify this function with any function on the circle. So we are basically working with functions on circle. Sometime we may have to work with 0, 2 pi. Because of that, we are just identifying these two spaces. Okay. In this, or you just work with circle, z power n on circle. These are functions. Z going to z power n is a function. Okay. Those functions n in z is an orthonormal basis for this. I'm saying you'll prove it later. We'll come to the proof later. We defined orthonormal basis. Any two elements are orthonormal, or we can prove it if you want, but we'll prove it later. Okay? That's all. Then I haven't said anything. I just said all these functions, z power n, they're just, I mean, it will lead to polynomials, and you can see that it is dense in C of that. Huh? Exactly. If you take linear combination, it will be polynomial. Polynomial in z and z bar. Z power minus n is just the z bar here because it is circle. Okay. We'll come to this. Before that, I want to talk about some properties of orthonormal basis for a general Hilbert space and come back to that. Okay.
So the need to be identified. You're saying this is an orthonormal basis for L2 0 to
0 to pi, yeah. Yeah. Theta going to e power I n theta, which is same as saying z power n. Here the function is e power I theta. Here the number, I mean, anything in S1 looks like e power I theta. This is just e power, I mean, z power n. Either you work here on circle with z power n, or work in continuous function on 0 to pi with e power I n theta. So we will come back to this. Okay, we'll come back to this. Before that, I wanted you start with the Hilbert space. H is some abstract Hilbert space. And we work with what separable Hilbert space. Okay, maybe I'll write a proposition. Proposition. H is separable. This implies any orthonormal set is countable. Okay. You can read it. If you have a separable Hilbert space, H is separable, then any orthonormal set is countable. Okay, proof. So if you have E and F in H orthogonal, okay. So there are two properties of orthogonal. I mean, you want to compute E minus F, distance between them, which is same as E minus F, okay, which is equal to EE1, FF1, but then F and G is 2, so which is equal to 2. You just compute this. E inner product E is 1 because it's orthonormal. F inner product F is 1, and the inner product between the cross inner products are 0. So it is just 2. Okay. So the distance between E and F is just square root of 2. Okay. So since Hn is separable, let Xn contained in H be dense subset. I mean, it's a, because it's separable, there is a countable dense subset. Okay. So then B of Xn, that is square root 2, no, square root 2 by 2, let's say take it, okay, can contain at most one of them. Let's say, let S be an orthonormal basis, let S be orthonormal, then B of Xn square root 2 by 2 can contain at most one element from S. Because The distance between any two elements will be root 2, less than root 2. Okay, but the distance between any two orthonormal element is square root of 2. So it cannot have more than one element. So it will have only one element. So, but then these sections are different, so it will be countable. Okay, this you can index it using this. It may not contain anything. Okay? That's all. So this implies S is countable. Okay. Okay. Just a remark. If x1 up to xn orthogonal, I mean, such that xi, xj equal to delta ij, okay, whether they are, I mean, they are orthogonal to each other, okay, then, no, not delta ij, equal to 0 if I not equal to j. Okay, I'm not assuming orthonormal. Okay, then summation xi square equal to summation norm xi square. You can easily see. Summation xi, you take summation xi, cross inner product will be 0, only this will remain. Okay, so equal to, what is less than or equal to? Orthonormal, yeah, orthogonal. Orthogonal to each other. When you have orthogonal to each other, this is true. Okay, this is just a remark. You can just calculate, but you need to take the square of that, not with norm. Okay, whenever in inner product, the right thing to take is inner product space, right thing to take is norm square. Okay, that's how you will work with. That's what you can, for computation, that's what you should use. Okay. So next proposition, very easy proposition, is any ortho, we need a ON, okay? ON, orthonormal set, is linearly independent. Okay. Is that clear? Proof. Summation alpha I, so that any orthonormal base, S is, I mean, suppose x1 up to xn, we need to consider linearly independent, we need to consider only finitely many linear combination. X1 up to xn orthonormal, okay? Suppose if summation alpha I xi equals 0, okay? But then you can compute this summation I equal to 1 to n alpha I xi with some xj. If you take the inner product, you will precisely get alpha j because everything else will be 0. Yeah, that has to be 0. That is 0. So this is equal to 0. So this simply this is equal to 0. Okay. Alpha j, because that is equal to 0, this is equal to 0. Inner product of any element with 0 element is 0 because of that. Okay. So you can do it, or you can try in some other way also. It will be.
Here are you saying that all balls will cover it, and then every element in S.
That's also true. Yeah, correct. Mm, yeah. Okay. Okay. So next proposition. So we have proved that if H is separable, then the orthonormal set is countable, and if any orthonormal set is linearly independent, we prove some inequality here. Okay. So let E1 up to finitely many, I think finitely many will do. Okay, it's an orthonormal set. Okay, I'm not saying it's orthonormal basis of something, just an orthonormal set. Inner product between any two is 0 if they are different. If it is equal, then it is 1. Any orthonormal set, then summation xei square then 1 summation you take x ei, I equal to 1 to n ei. This is like taking the component. Okay? If you have something here, you will take the component in the x-axis. It is like taking the inner product with this, taking the inner product with like this. So it is like there are some n axes are there. You are just taking the component, okay, ith component. So that is what is this. Then it is just the vector, orthonormal vector. If you have any element here, this is, if you have, this is the x is this vector, this point. Then you take this, and if you have E1 is this vector, E1 is 1, 0 or 0, 1 or whatever, then this component times this vector, component times this vector will give this vector. You know, in 2 dimension and n dimension. That is precisely we want to do. We want to do in infinite dimension or any Hilbert space. So I am just taking this. Okay? This is ortho. No, I am not talking about. Wait. Let me think about the statement. Okay? I didn't write it, I believe. Yeah, this is orthonormal to ei, ej for all j. No, wait, x minus this. Then 1, x minus this is orthogonal to ej. Okay, that's all. That's what I want to say. Okay, 2 summation this ei square I equal to 1 to n, okay, is less than or equal to norm x square. Okay, proof. 1, this is just a calculation. You just take inner product. This is this xej. If you take the inner product with this, for any other I not equal to j, it is 0. Only the jth one it will pick up, and that is exactly xej. That minus this is 0. Okay, exercise. It's clear. Okay, in this inner product with ej, xej. Here, if you take it ei only with I equal to j, it will pick up, and that will be ej is inner product is 1. This is scalar. Okay, and you will precisely get this, and that is, okay, that's what you will get. Xej minus xej is 0. Okay, so this is exercise. Here, x is in h. Okay, h is everything. Okay, x is in h. You want to use another notation, xi, eta or something? Okay, x, it's saying whatever is written clearly. Okay, x is in h. X is in h. X minus, these are vectors, these are scalars. This vector multiplied by the scalar, you have the summation. Okay, x minus this is a vector. This vector is orthogonal to ej. X, you can add, subtract 2 things in vector space. X is a vector. X, ej, ei. It is like saying that if you have something like this, just take one vector, x, then you take e1, x e1. If you subtract it from x, that will be precisely that, but that will be, okay. That's what this says. Exercise. And I told you the proof. You just write down the proof. Okay. 2. So you want to prove that. So now we have x minus summation x ei I equal to 1 to n. Okay. Is ortho. So what do you want to prove? Yeah. Is I mean, yeah. Is orthogonal to ei. Ej we have for all j. Okay. Now what do you want? Norm x square equal to norm x minus that plus that. Yeah, x minus x ei. We don't need this. I'll just come to that. Okay. X equal to x minus summation x ei. Okay, plus summation x ei. Okay. Now this is orthogonal to each ei, so it will be orthogonal to this. Okay, this is orthogonal to this. So if you take the norm x square equal to, you call this as z. Okay, Call this as Z. Norm Z square plus summation mod of x ei whole square. Is that clear? All these elements are orthogonal elements. These have ei multiplied by some scalar. Okay, I equal to 1 to n. That will be, they are all orthogonal to each other. And this is orthogonal to that. That's what proved in the first statement. Okay, so norm x square equal to this square plus each one of them square, each one square. So that is equal to this. Okay. So this implies exactly that. This is something positive. So this implies summation mod x ei square is less than or equal to norm x square. Okay. So these are the two statements. If you take any x, you take the component with respect to some ei, multiply with that ei, take this sum. If you subtract that from x, that is orthogonal to all those ej's. Okay. Because of that, it follows that summation I equal to 1 x ej square equal to norm x square, less than or equal to mod x square, because it is some positive number equal to that. If you have a problem, if you don't understand anything, you tell me. Is that something? If something is not clear, okay? Except everything is packed, it's clearly written. Okay. Okay. Now proposition. Let En n in n be orthonormal set in H. H is separable. Okay. So it is any orthonormal set is countable, separable. Separable Hilbert space. H is some separable Hilbert space. So any orthonormal set is countable. Yeah. Here. Yeah, I'm reading. H is separable Hilbert space. E1, En, n in n, this is n. Okay. Be an orthonormal set in H. On means orthonormal set. On set, orthonormal set in H. Okay. Then summation n equal to 1 to whatever, if it is countable, suppose if it is infinite, otherwise you take finitely many of them. This norm xen square is less than infinity. Okay. That's all. This is summable. Proof is clear. Summation n equal to 1 to n x en by the earlier proposition is less than or equal to norm x square. Okay. For all n. Okay. Implies whatever. That's all. Just take limit n going to infinity. Okay. We have already proved that summation n equal to 1 to n x en is less than or equal to norm x square. Separability is so that any orthonormal set will be countable. We will work with separable Hilbert space. Non-separable Hilbert space, people are working in physics. In mathematicians don't work. I don't know. Well, in physics, people work on that, but I don't know where. I haven't understood. Okay. Yeah. Finite too. You take finite sum. That's what I said. You take a finite sum. Okay. If it is infinite, this is true. Finite, there is nothing to prove. Okay. Because summable statement is about summability. So for infinite one. Okay. Okay. There is a corollary to this. People must have worked on this for a long time. For Fourier series, this is what is called Riemann-Lebesgue lemma. But at that time, functional analysis may not be there. If you have any x in H and En, n in, well, it should be orthonormal. I mean, if it is infinite sum, I mean, if it is infinite, otherwise there is no convergence. Okay, it's an, well, let's assume that it is infinite. Okay, orthonormal set. Okay. Then xen will go to 0. Okay. Well, I have said n, but we will be taking z. I hope there is no confusion with that. We will be working with z. I mean, our orthonormal basis will be indexed by z for our example. I said e power I n theta, no? Z power n, I just gave the example. That the orthonormal basis is indexed by z, but that's okay. The convergence, you can understand the convergence. You just have to take mod n or something. That's all. N in z. Okay? We will explain that. Okay. This is because the series is convergent. This goes to 0. That's clear. The element has to go to 0 when the series is absolutely convergent. It's because of that. Okay. This is what is called Riemann-Leibniz lemma in Fourier analysis. Okay. Good. Okay. Okay. Now slightly non-trivial. Till now, I think the concept may be non-trivial, but the proof is trivial. There is nothing is involved in this. Okay. Now we have to listen little bit. Okay. So this is the proposition. Okay. The following are equivalent. The following are equivalent for some alpha n, n in n. Okay. Alpha n is some number in complex number. Okay. The following statements are equivalent. 4 statement or 3 statement, I don't know. 1, summation. I have to start with this H Hilbert space and En n equal to 1 to infinity contained in H is orthonormal. Okay. You have an orthonormal set En, then the following are equivalent for any collection alpha n, any sequence of numbers alpha n, complex numbers. The first statement is summation alpha n En converges. Okay, this is an element of Hilbert space. Okay, if you take the linear combination, but you are taking infinite linear combination, so you have to say it is convergent. Finite linear combination, there is no problem. When you are taking infinite linear combination, you have to invoke the topology and it has to converge. Okay, so it converges. That is, we are assuming always H separable and we are working with always. Okay, from here onwards. Okay. Okay. Well, we will either work with, I mean, the converse is also true. I didn't say because I didn't define orthonormal basis or something. The converse is also true. You can take rational linear combination of, if you have a countable orthonormal basis, then a countable orthonormal basis, you have to talk about basis. Then the Hilbert space is also separable. You can take just rational linear combination of those orthonormal basis, that will give it. Okay? That will give the dense subset. Okay, the second statement is summation n equal to 1 to infinity. This is just about numbers, complex numbers. Okay. Then the third one is what? Just I think it is a closure. Yeah. Span of. I was wondering whether there is something in between. Okay. You have seen it somewhere? No. My class. You saw it. Okay. That's what I thought. If the work video is not working, I was about to post that. Because I have done it in 23. So it's the same thing. I'm repeating. Okay. X in span of En, n in n. Okay. Closure such that X En equal to alpha n. See, if you take this, if you take inner product with any En, you will get alpha n. If you take this vector, this converges, so this is a vector in the Hilbert space. If you take inner product with any em or something, you will get exactly alpha m. Otherwise, you'll give and the inner product is continuous because of that. Okay, we'll come to that. But then this statement may not imply that. I mean, if you take something in the span is just linear combination of these things that converge to some x. Does not mean it has to look like an infinite sum like that. There is no reason. But in Hilbert's space, that will be guaranteed. Okay, let's come to this. So I thought that's all. Proof. Okay, summation alpha n en converges. So 1 implies 2. 1 is equivalent to 2. You will prove 1 equivalent to 2. Okay, summation alpha n en 1 to infinity converges. That is, it exists, which is equivalent to saying summation n equal to 1 to n is n is n up to n converges as a sequence, which is equivalent to saying it is Cauchy. So it is equivalent to saying n to m en converges, goes to 0 as n and m goes to infinity. Okay, this is okay. Yeah, maybe n equal to n to m. Okay. Okay. This goes to 0. This is equivalent to saying norm square of this goes to 0. Something goes to 0, if and only norm goes to 0, if and only norm square equal to 0. Okay, which is equivalent to saying summation, but this is just orthogonal vectors. So this is same as summation alpha n square n equal to n to m goes to 0 as nm goes to infinity, which is equivalent to saying summation mod alpha n square is less than infinity. Okay, all those things are same. Okay, so see, this is the nice thing about Hilbert space. Usually, if it is absolutely convergent, something is absolutely convergent, summation norm xn is finite, then you know that summation xn, when the space is complete, summation xn exists. But summation xn exists doesn't mean this is true. But in Hilbert space, if you have an orthogonal sum like that, this will imply the square will be square is absolutely convergent. Okay? That's something about Hilbert space. Okay. So 1 implies 1 is equivalent to 2. Okay. Now either 1, 2, whatever implies 3. That's what we have to prove. Okay. So there exists an element in X such that that is clear. I mean, if this is true or this is true, then if you take this is the X. Okay. Take X is equal to summation alpha n en, which exists. If you take X en, okay, which is summation alpha n en equal to 1 to infinity. I mean, you are using that fact. That is why I'm saying em or whatever. Okay, you can take the inner product out because I mean, did we prove inner product is continuous? We haven't proved. No, inner product continuous will follow from Cauchy-Schwarz inequality. Okay, inner product actually, I am only taking one at one variable, which is a linear linear functional. If you fix one variable, if you take it, it's just linear functional. You have to know it's bounded linear functional. For that, you need only Cauchy-Schwarz inequality. If you use Cauchy-Schwarz inequality, the norm will be norm of this. You just work it out. Okay, it's an exercise that inner product is continuous. Inner product is continuous in both the variables, two variables together. Xn goes to x, yn goes to y. Then inner product xn yn will go to inner product xy. You can prove it by using triangle. I mean, there is not much triangle inequality and Cauchy-Schwarz. These are the two things you use and you will get it. It's an exercise. Maybe I will give it in assignment. Okay. Inner product is continuous. Product is continuous. Okay. That is, if xn goes to x, this is what you have to prove. Yn goes to y. Okay. Then inner product xn yn will go to inner product of xy. Okay, easy. Okay, it's clear. It's easy. Triangle inequality and quotient showers, from that it should follow. There is nothing else to use. Okay, nothing else you have. Okay, so because of that you can take it out. Okay? Because of the inner product is continuous, you can take that out. Okay, then it is just alpha n. You have alpha n here and en em, and only for n equal to m only it will survive, and that is equal to alpha n. So 1 and 2 implies 3. I mean, from 1 2 you want to get this statement. Okay, that is you take it here and then take x equal to that, and that inner product is alpha n. Okay, so 1 2 implies 3. Well, now we have to prove 3 implies either 1 or 2. Yes. I mean, you have to prove this, and okay. So now 3 implies 1. 3 implies 1. So exactly that it follows from this, right? Summation xen converges. Summation alpha, I mean, it is just clear, no? Xen equal to alpha n. Okay? We know that summation xen square is less than infinity. That's all. We already know that. That's all. Okay? For any x and en, that is true. Okay, we have already proved it. We already proved. Okay, so the next proposition. So this is a whatever anything which satisfies this condition, equivalent condition, is what is called an orthonormal basis. Okay, H separable Hilbert space. Okay, the following are equivalent for En. N in N. For En or what? Let me see. 1. Yeah. En, N in N is a maximal orthonormal set. That is, that does not exist a set, bigger set, set containing this, which is orthonormal. Okay? That's clear, no? The meaning is clear. That is what it means by maximal orthonormal set. That does not exist a bigger set that does not, I mean, if there is a set which contains this and it's orthonormal, that has to be equal to that. That's what it means. Okay, maximal orthonormal set. Okay, then x is equal to summation x en en. The equivalent statement. Okay, 3 xy equal to summation x en eny. Huh? Anything which satisfies this condition is what is called an orthonormal basis. Okay, this is for all x in H. This is for all xy in H. Okay? If something satisfies this condition for all x, for all xy, yeah, any one of this equivalent condition, orthonormal basis. Okay, then 4. Okay, then 4 is some norm x square equal to summation x en square n equal to 1 to infinity. Okay, here inner product between x and y equal to n equal to 1 to infinity sum x en en y for all x and y in x. H. For all x, y in, yeah, E, H. Okay, so proof. So En is a maximal orthonormal. 1 implies 2. Okay, we have to use it's an orthonormal set. Okay, if it is an orthonormal set, we know that Xen converges. Okay, we know, I mean, since En is orthonormal, okay, summation Xen En converges. Okay, so if X is not equal to summation Xen En, okay, then take y is equal to x minus this Xen En. Okay, then this y is orthogonal to En for all n. The same idea, right? Huh? Orthogonal to En for all n. Okay, so this y by norm y and En, comma En, all those En is orthonormal set which contains En. Okay, contradicts maximality. Okay. Which contradicts the maximality of the set. We have assumed it's a maximal orthonormal set, so this cannot happen. So this is equal to this. So this implies x is equal to summation x En En. Other things are just if you have this, you take inner product x and y, you just apply this xen, summation x, some other em or something. Only when n and m are equal, they will pick up. Otherwise, it's 0. That will be 1. It's precisely this. What is it? Hypothesis? Uh, yeah, we start with an orthonormal. Correct. En orthonormal. You are right. Yeah, we start with an orthonormal. Correct. Yeah, we start with an orthonormal. Yeah. Then it is maximal if this happens. So this is equivalent to xy is this, and it is just x equal to y. That's all. This is just x equal to y. X equal to y. This is just the bar of that, and that will become this. You just take the inner product of x, summation this, okay, then double summation. You can take both of them out. Okay, only when xen and em, they are equal, n equal to m, otherwise it's 0. And en is norm 1. So you will just only get this. That's all. Okay, and 3 implies 4 is just x equal to y. So 4 implies 1 is what we have to prove. Okay. Oh, sorry, I have erased it. Well, I hope you have written it. So, okay, I will go here. Yeah. Thank you. Good. Okay. So now 4 implies 1. Okay. So 4 implies 1. So we have to prove that it's maximal. Suppose not. Okay. Suppose, I mean, we are assuming 4. Okay. Assume 4, which is norm x square equal to summation norm x en mod square n equal to 1 to infinity. Okay. And suppose en is not maximal. then there exists a E in H such that En is orthogonal to En for all n. Okay. Okay. And norm E equal to 1. You can just divide it by the norm if you want. Okay. Now E, but this says that norm E square equal to summation En square by 4, if you assume 4. But this is equal to 0, but this is equal to 1. Okay. So it has to be maximum. Okay. Contradiction. This is a contradiction. Okay.
What polarization do we need to assume the orthonormal?
Orthonormal we are assuming.
Do we need?
Yeah, otherwise how will it perform? Yeah, norm x equal to this. It is about orthonormal. Some E is ortho. 4 implies? No, 4 doesn't imply En is not orthonormal. Some said something is equal. Why does it? Xen is just some complex number, no?
For all x, this is does it imply that
for all x? Yeah. For all x, this is true. Yeah. I think so. Huh? Yeah, if you take x equal to En, then En, yeah, exactly. Yeah. Yeah. Okay. So finally, one corollary. We have already know that if En, so anything we satisfy definition. I mean, we have already defined what is an orthonormal basis. Okay. Any corollary, further remark. If En is maximal orthonormal, then span of En equal to H. That's what we wanted to, which is clear, right? I mean, it is just the span closure of En is H. Okay? Because finite linear combination you take and you can write it like that. This is clear. Okay. So what do you want to say? Yeah, this is En is an orthonormal basis. That by our earlier definition. Orthonormal basis. En is an orthonormal basis. Okay. Okay. I have time. Okay. Okay. So now let us take C0, 0, 2 pi. Okay. In this, maybe proposition, H is equal to this, and not H is equal to this. You take H. I want to take the pre-Hilbert space. Okay, let's take L2 itself. Okay. L2 of S1, Z power n, okay, n in Z, okay, contained in L2 of S1, or e power int, okay, I mean f of t equal to e power int, n in Z, contained in L2 of 0 to pi, is an orthonormal basis. Okay. So why is it an orthonormal basis? Proof.
Okay.
Z. Okay. Yeah. So you take first, you need to prove orthonormal basis. First, they have to be orthonormal. Okay. So if you take whichever you want to take, both are same. Okay. It's clear that both are same. Is Z power n, which is e power int. Both are same function. Okay.
So what e to the I perhaps so complex number, right?
Right. Yeah.
There you are saying it's 0 to 2 pi.
No. This is 0 to 2 pi. The values are taken in complex number. It is defined in 0 to 2 pi. range is complex number, complex valued function. L2 of you take continuous functions on that, complete it. Yeah, that's all. Okay. You take continuous functions on circle, S1 is circle, complete it with respect to the inner product, Fg bar inner product, integral Fg bar, this inner product. You complete it. What is E? E is the number. T, function. T going to e power int, function. E power int is the function. F of t equal to e power int. N in Z, varying. For each n, you have a function. Set of functions, right? So it is contained here. So this is space of functions. So it is set of functions. Okay. This is space of function, L2 0 pi. So it is set of functions. Okay. Okay. So let's work with this. Anything we can work with this. Integral 0 to 2 pi e power int. I mean, let's call Fn or En equal to e power En of t. So since you asked e power int, okay. So where is the rest? En Em, okay, equal to integral 0 to 2 pi e power int e power minus imt. It's the bar, right? Fg bar, the bar is minus. Yeah, that is equal to 0 to 2 pi e power I n minus m t dt. Exactly. So that is equal to e power I n minus m t by I into n minus m. Okay, which is equal to no, you need a 1 by 2 pi, which is you need to take a 1 by 2 pi. You can define the inner product to be 1 by 2 pi. Maybe I should have said it. On L2 0 pi, okay. Yeah, you have to take 1 by root 2 pi. That will
take 1 by 2 pi.
Yeah. So okay, let's come on L2 0 2 pi. Define the inner product between f and g to be 1 by 2 pi integral 0 to 2 pi fg bar. Okay. I take a 1 by 2 pi. Okay, I mean, you can multiply by a constant, still it will be inner product. Yeah. Fg bar, inner product Fg bar. Integral is over the S1. Huh? E power theta. So that is why we will do it. We will convert it here and then take. We can, then you can take it here and, I mean, it is basically the line integral, but you can work with this to define the integral. Exactly. You can identify with function here and do this. That is why we need the 0 2 pi. Okay, which is easier. Which is same thing, same the line integral on that. Okay, yeah. So if you take that, then that is equal to, you have a 1 by 2 pi here, 1 by 2 pi here, and that is equal to 1 if n equal to m equal to 0 if n not equal to m. It takes the 2 pi and 0, it takes the same value. Huh? Usual? Okay. Then some. Okay. This was the question. But finitely many. Okay. Okay. So this shows that that's a orthonormal set. Okay. We have to show its orthonormal basis. Okay. This is 2, that is 1. We need to prove summation alpha n en, n in z, n equal to finitely many of them. Okay. Okay, that is okay. Span of En. Span of En, n in Z, they are, okay, now you can look at it Z power n if you want. Okay. Huh? No, wait, span of this. Okay. So this is an algebra. Call it as EA. This is an algebra. I mean, if you work with 0 to pi, there will be a confusion. So we can work with the circle. Okay. Or you can take this, which is isomorphic to same thing as span of Z power n, n in Z. Okay. N in Z. You call this A, which is contained in C of S1. Okay. This span, this is an algebra, contains constant, contains conjugate because it's taken over Z, contains constant. So Stone-Weierstrass implies that A is dense. C of S1. Okay. So this implies that, I mean, the same topology, everything. Okay. This implies that En n in Z span is dense in our C0, 0, 2 pi, if you want. Okay. Span is dense. Span is dense. Okay. Span is dense. Okay. What does it mean by, if you have any function here, you can approximate, you get a sequence here which converts to that. Okay. So there exists, so you call this as again A. Okay. So if you have F in here, C0, 0, 2 pi, okay, there exists Fn in A such that F1 converges to F uniformly. Okay. But then this implies F1 converges to F in that norm, in that inner product, whatever the inner product, L2 inner product, which is usually we denote it by L2. The convergence is in L2. Okay. Let me explain. Yeah, ask me. Stone-Weierstrass implies that this Z power n that is dense here, which is same as saying En is dense in 0. This is 0. It's the same thing. Okay. Now I am saying that, so you call that algebra as A. Okay. Now if you have any function here, there exists a F1 such that F1 converges to F uniformly. That's what I am saying. F1 from that A. But uniform convergence imply that L2 convergence. This because uniform convergence, you can take the limit inside. Okay. We have seen it. If F1 converges to F uniformly, integral F1 will converge, integral Fn minus F. This implies, let's write it like this, implies integral 0 to 2 pi, maybe 1 by 2 pi, mod Fn minus F whole square d, whatever, d. This goes to 0. Okay, this is okay. This goes uniformly. Fn converges to F uniformly. Then you can take the limit inside, this goes to 0. This is the dominant convergence theorem, or I mean, this is much stronger than the uniform convergence is stronger than that. Okay. Dominated convergence, you need much weaker condition. This is stronger condition. Okay. So this we have used several times, the earlier course and in this course. Uniform is not proved for Riemann integral. Yeah, for Riemann integral, you must have proved, no? That's what we are using. This is Riemann integral only. No, dominated I used without proving it, but for uniform it's proved. So that's what we are using. Okay. So uniform limit, you can take it inside. So because of that, this is true. So this implies A is dense in L2, right? I mean, A is dense in 0 to pi. A closure will be C0 to pi closure also. If S is contained in some S prime which is contained in some X, and S prime closure is that X, this closure will also be that. Okay, that we have used some time back also. So because of that, this is dense. So these things prove that it's an orthonormal basis. Okay. Now we prove an important theorem in Fourier analysis, which people must have worked for a long time, centuries ago. Huh? Say it again. When did we start? Oh, this is 1 hour 15 minutes. We started a little bit late. Okay, that's okay. Okay, we'll stop. Whose purse is this? Huh? Yours. No, I thought I have 15 more minutes. So